This video is an informal introduction to the syntax of the logic of relations, part 1. Here are 3 examples of relations. We obtain a relation by beginning with a complete sentence and deleting terms that designate individuals. So for example, here number 1 might have said Socrates is a philosopher. We have deleted the term Socrates that refers to an individual to create the relation blank is a philosopher. Likewise, number 2 might have said 3 is greater than 2. We delete the individual terms that designate individuals, like the number 3 and the number 2, and we get a relation with 2 blanks. Blank is greater than blank. And finally, in example number 3, our sentence maybe was Jane nominated John for president, and we obtain a relation in this case by deleting all of the 3 individual terms to get blank nominated blank for blank. So a relation has empty spaces in it that are to be filled in by terms that designate individuals, or if we want to just indicate that there is a blank, we're going to use a variable. A variable is going to be the analog of a blank. So for example, we could say X is a philosopher, or X is greater than Y, or X nominated Y for Z. And so in our language, we're going to reserve the letters X, Y, and Z at the end of the alphabet as variables. And variables, it's going to turn out, can take constants as values. Before we talk about constants, let's just be clear about how we build an interpretation when we specify the meaning of a relation. So for example, we'll write Px, X is a philosopher, or Gxy, X is greater than Y, or Nxyz for X nominated Y for C. And it is a convention that we follow to use the variables in alphabetical order. So we always use X before we use Y, and we always use Y before we use Z. Constants, as we've already said, designate individuals. So for constants, we're going to reserve in our language the lowercase letters at the beginning of the alphabet. We're going to call these constants. And to build an interpretation, we specify the meanings of the relations, and we're also going to need to specify the meanings of the constants. So for instance, maybe the letter A refers to Alice, the letter B refers to Beto, and the letter C refers to Carlos. And in that case, we can use these constants and the relation Px, X is a philosopher, to symbolize simple sentences like Alice is a philosopher, which will just be PA, Beto is a philosopher, would just be PB, and Carlos is a philosopher, would just be PC. And now each of these sentences is going to be a sentence in the formal language of LR, and they're going to be atomic sentences. They are also going to be sentences that have determinate truth values. So any sentence like PA is going to be determinately either true or false. Here's another sample interpretation, and we'll use it to make a couple of observations about how we symbolize in the logic of relations. So suppose we have the relation X is greater than Y, and the letter A designates 1, the letter B designates 2, and the letter C designates the number 3. We can symbolize a lot of different statements. For instance, 2 is greater than 1. And the way we do that in our convention of writing down relations, we always write the relation letter first. So the relation letter is G. And since it is the 2 is greater than 1, that's GBA. Because B designates 2, so the B has to go in the first place where the X appears, because it's X is greater than Y. And so the A in this example has to go in where the Y is, because the relation is X is greater than Y. If, on the other hand, I was symbolizing 1 is greater than 2, I would write down GAB, because the relation is X is greater than Y. So this GAB says A is greater than B. A is 1, B is 2. So this is the correct way to symbolize 1 is greater than 2. And I can just continue down the list here. 3 is greater than 2. That's going to be GCB because C is 3. So this says C is greater than B. 3 is greater than 2. That's what the sentence is that I'm symbolizing. Now, suppose for some reason I wanted to symbolize the sentence that says 2 is greater than 3. I could do that. I would just write down G, B, C. And finally, suppose for some reason I wanted to symbolize the sentence 2 is greater than itself. Well, since its x is greater than y, I can simply put in the constant b for x and the constant b for y. So 2 is greater than itself would be GBB. Now, you and I know that some of these statements in arithmetic are false. For example, 2 is not greater than itself, and 2 is not greater than 3. And that just means that we would assign a truth value of f to the statement GBC on this interpretation. Okay, so statements like GBC, which are sentences in the language of LR, will now have truth values on a given interpretation. But the formal sentence GBC doesn't have a truth value unless and until we specify an interpretation. So let's make a couple of quick observations here. First, order matters. We never assume that order does not matter. So if we have a relation that's X something blah, 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 Y, we always symbolize things in that order, and we never assume that GBA means the same as GAB. Some relations will have that property, but in our system, we'll always explicitly state that property of a relation. The second thing to notice that's quite important is that X and Y, or any variables appearing in a relation, are to be filled in independently. So X and Y take constants as values independently. And what that means is that they can take on the same value or they can take on different values. So for instance, in our last example here, we could put B in for X and we could also put B in for Y. And there's nothing wrong with that. We can do that. Now, it just so happens that in arithmetic, the greater than relation is not a relation where any statement is true when you fill in the same thing for both places. There's a technical name for that. That means that the relation is not reflexive. But again, we're not going to assume anything about the relations we're symbolizing. We're going to leave it to whoever is presenting us an argument with the relations to explicitly state whether the relation they're using has any special properties like reflexivity. Now we're ready to take on symbolizing slightly more interesting sentences that we're going to call truth functional compounds. And you'll see why they're called truth functional compounds here in just a minute. Suppose we're using an interpretation where Px says X is a philosopher, Lxy says X likes Y, and then A, B, and C designate Alice, Beto, and Carlos respectively. We can now symbolize things like this. Alice likes Beto, but Carlos does not like Alice. And we can take this just one piece at a time. We recognize from previous work that you've done in the logic of propositions that what's going on here is that we have two sentences joined with the word but, which we know means and. The first part is Alice likes Beto. Notice that that's going to be L-A-B and not LBA. LBA would say Beto likes Alice, but we don't want to assume that just because Alice likes Beto, it's also the case that Beto likes Alice. So Alice likes Beto has to be symbolized LAB. The second part of the sentence here, Carlos does not like Alice, is the denial of a claim. It says that it is not the case that Carlos likes Alice. So we're going to say, and it is not the case that Carlos likes Alice. And that is a complete and correct symbolization of the sentence, Alice likes Beto, but Carlos does not like Alice. LAB and not LAC. I'm sorry, LCA. The second one says, Alice is a philosopher who likes Beto, but does not, oh, sorry, but not Carlos. I got ahead of myself there, right? So Alice is a philosopher who likes Beto, but Alice does not like Carlos. I was already paraphrasing in my mind to make sure I didn't make any mistakes when symbolizing this. So what's going on here is that you have to be able to parse this sentence in English and say, what is the main logical truth function that this sentence is expressing? And the main logical truth function is conjunction. This is a conjunction. This is going to say and here. And the first part says, Alice is a philosopher who likes Beto. So now how do we symbolize this? What do we do with this who? Well, we just have to think about how to paraphrase this using the relations that we have access to, right? So this says two things. It says Alice is a philosopher and Alice likes Beto. And you want to be really careful with this. You don't want to sort of assume that who always becomes an and. Uh, you want to really express what this sentence says using the relations and truth functional connectives, okay? And the truth functional connectives are the five logical connectives from the logic of propositions. So what I said was that this says Alice is a philosopher. Alice is a philosopher and Alice likes Beto. That's what it is to say that Alice is a philosopher who likes Beto. And Alice does not like Carlos. So, and it is not the case that Alice likes Carlos. So this is not that different from symbolizing in LP because if you notice, all of our sentences are simply compounds made up of atomic sentences in LR that do not contain any variables. We will be using variables to symbolize, and we will cover that in part 2 of this video. But before we go on to that, let's look at the last example. If neither Alice nor Beto is a philosopher, then they both like Carlos. Well, going back to the logic of propositions, this is a simple if-then statement. So we know the main logical connective is going to be an arrow. And the first part of the arrow, that is to say what we call the antecedent, is neither Alice nor Beto is a philosopher. So this says neither Alice is a philosopher nor Beto is a philosopher. And so a simple way of doing that is to say it's not the case that either Alice is a philosopher or Beto is a philosopher. Now that's the antecedent, and the entire sentence says if this is true, if neither Alice nor Beto is a philosopher, then what? Then they both like Carlos. Well, that says two things. Then that says that Alice likes Carlos and Beto likes Carlos. So then Alice likes Carlos and Beto likes Carlos. And these are some simple examples. They're getting more challenging, but as you'll see in the next video, they're simple because they don't involve any variables or any generality.